warm welcome to all the participants and the guests for the 2 weeks AICTE FDP program in recent trends in signal and image processing using MATLAB. This program is being held in 2 sessions, one offline and one is online. So we have completed successfully 1 week online session in the last week, and now today we are going to start the next offline session from today onwards. So today's session speaker, I want to invite Dr. Narasimhulu sir, Principal of LIET Institute of Engineering and Technology. Sir has received PhD from JNTU Kakinada University and MTech from NIT Calicut and BTech from SV University Tirupati. Sir is having 27 plus years more than teaching, research and administration. Different capabilities sir has served, and he is serving more than 18 years. More than 18 years sir has served various administration roles, and sir has guided more than 4 PhD students, and still 4 PhD students have been guiding by the sir. Sir has published, he has published 6 patents, 54 papers in various international and national journal conferences, including Scopus Index, Web of Science and various conferences. Sir has received various grants, including from SCRB, and he has organized various FDPs, workshops at national and international level. Sir has been a senior member of IEEE, and he has been a vice chairman of IETE, and he has been invited to the various conferences, FDPs, as a session chair. He has received Best Principal Award for this year from LIET Institute of Engineering and Technology. Sir has received even Best Researcher Award. So today's session, sir will be taking on signals and systems, so that we will be having a great knowledge from the sir and various capabilities. So I invite Dr. Narasimhulu sir to take over the session. Thank you, sir.
Good morning to all participants. So this is the 7th day in our entire 11 days ATAL FDP program. I thank each one of you for extending your support for all these 6 days in attending good number. And today also you have attended in good number, so we are very delighted. And today I will be talking on the topic of concept of orthogonality. So as the FDP title is Recent Trends in Signal and Image Processing using hands-on session with MATLAB. So I have chosen the fundamental topic in signal processing is orthogonality. For any transform, orthogonality is the basis. You name any transform, the basis is concept of orthogonality. So this topic is covered for undergraduate students in their signals and systems course. So which is the course itself is a fundamental and prerequisites to several other courses like digital signal processing, image processing, speech processing and video processing, all other analog communication, digital communication, several courses. This is a fundamental course. So though it appears to be a very simple and fundamental topic, I feel that it is useful to you all. So hence I have chosen this topic. So here, the concept of orthogonality you have heard from the vector also in our undergraduate or intermediate courses. So there is an analogy between vectors and signals. So all ECE faculty members might have known where they have studied. The analogy means similarity. Okay? So when you deal any new concepts, new theories, we generally focus on the what we have learned earlier. From the past, we can compare, we can see some similarities. So this vector theory have been evolved some 100 years back. So later signal concepts and functions concepts has come. Okay? Don't think that signal and function both are same. Okay? Function may have the multi-valued, signal is a single valued. Signal is a function which has only single value. Function means it may have multiple values at same time. Right? That is the basic difference between signal and function. Right? So here, as you all know that the concept of dot product. Right? When two vectors are fundamental, two vectors are perpendicular, it means both are mutually independent. So one vector doesn't depend on others, or one component you cannot see in other vector. Similarly, other vectors components cannot be seen in this vector. So totally they are independent. So if you draw a structure, you have seen it appears like a 90 degrees between them. If two vectors having 90 degrees between them, then we say that those two vectors are perpendicular and one is independent of another. Okay, let us say V1 and V2 two vectors, V1 and V2 two vectors. So these two vectors are perpendicular, V1 and V2 having 90 degrees, then we say that V1 dot V2 equal to 0. It is the theory what we have learned. Okay, the dot product between these two vectors shows 0, means those two vectors are independent and perpendicular to each other. So now this concept, this analogy, we are extending to the signals. Okay, so in the signal processing theory, we cannot use the word dot product. We use there another word called inner product. Similar word for the orthogonality or perpendicular, inner product. Inner product should be 0. The similar word to the dot product in the signal or function independent, we use the word like inner product. The inner product between any two functions or signals is 0, then they are said to be orthogonal to each other. So then now what is that inner product? This concept we will explain through approximation of a one function with another function. From there we derive this concept. Right? So approximation of one function with another function. Dot product. We use there another word called inner product. Similar word for the orthogonality or perpendicular, inner product. Inner product should be 0. The similar word is dot product in the signal or function independent. We use the word like inner product. The inner product between any two functions or signals is 0, then they are said to be orthogonal to each other. So then now what is the inner product? This concept we will explain through approximation of one function with another function. Now there we derive this concept. Right? So approximation of one function with another function. The same equal, suppose 99 rupees is not equal to 100 rupees. Right? We want to have 100% approximation on equal. So generally, now as we see in the currency notes, you may not have in signals and functions. So that is why possible extent we want to approximate this function with another function. So why we are using this function? Suppose in the laboratories, suppose if you don't have this function, if you want to use some equivalent function, then it will be useful. Right? So here, f1 of t is approximated with c12 to f2 of t. Then the error between these two functions must be minimum. Then only we can say that this function is just approximate. When you say that this f1 is just approximated in terms of f2 of t, the error between these two must be as minimum possible 0 or as minimum as possible. As minimum as possible error. Then only it is going to be just approximation we can say. So now we have to calculate the error function. The error between these two, FE error equal to f1 of t minus c1 to f2 of t. This is the original. So you are approximating this. Now approximating this on this. This minus this will give the error function. Right? So now you have to choose or define or decide or calculate this constant or coefficient. This is called as approximation constant or approximate coefficient or constant you may call, right? Such that this error must be minimized. Error must be minimized. You have to choose this approximation constant or coefficient such that f of p is minimum. It should be minimum. So now, how to minimize this error? How you calculate this? It is error function. It's not error. It's an error function. So this error function must be minimum. Right? So in this error function minimization, so now we have to use here statistics. So how you express the error? One way is what is the total error? R with respect to time. What is average error? Average error or mean or average or mean error. We have to calculate the total error divided by time. So mean error. So now the error comes we have. So how we find out total area divided by time? Error function. This is the error function. Let us say f of t. This error function is there. Suppose let us say here some p1 to p2. This is error function of these two. The difference between these two is error function. Now I want to calculate average error from this function. So you need to calculate this area divided by time. You will use the mean error. So how do you calculate the area of any function? By using integration. So integral of t1 to t2 f of t dt error function error function area under error function area under error function by using this integration. So we calculate this integration. We calculate it. We use this integration. We get the area under this curve. Now we want to calculate average error. Means area divided by total time. So total time is 1 by Q2 minus T1. This is what we call average error or mean error. Mean error is equal to area total error divided by time lapse. It means T1 to T2, T2 minus T1. This is the area divided by this will give average error or mean error. Now statistics are saying that depending on average error or mean error doesn't look nice. It gives sometimes wrong estimations. Why? That I will tell you through an example. Through an example, there is what is it? Yeah. See, I have one sinusoidal signal 0, pi, 2 pi, let us say 1 minus 1. Let us say it is a sin t, for example. I want to approximate sine t with a null function 0, pi, 2 pi f of t equal to 0 always with respect of time. With respect of time, its value is 0. It's a null function. Null function. Suppose if I approximate my sine signal with null function by multiplying some constant C12. C12 into 0 is also equal to same 0. So then my error function is what? My error function f1 of t minus
F2 of C.
so what do you get? Error. What do you get? Error.
Sinusoid.
This minus this again you get
Sinusoid.
sinusoidal signal 0 pi
2 pi.
2 pi. This is my error signal. If you find the area which average error, it is a positive area, here it is a negative area. If you sum up total area under this curve from 0 to pi and pi to 2 pi, this will give positive area, this will give negative area. If you sum up, you will get
0.
0 area. So your area will become 0, means error. It shows that average error equal to 0. Error equal to 0 means what? Your approximation is correct. But whereas this function is different from this function. There is no comparison at all between these two functions. It is simply null function, it is a sinusoid.
Sinusoid.
How this function is approximated with this? Even suppose you could have been like a rectangular function or square, then you can say that there is some comparison. It is after all a null function, so all values is 0, whereas it is sinusoidal. If you see its average error, it shows that these two are approximated properly. So hence, choosing mean values for this kind of estimation is wrong. So then we have to go for mean square error. Rather, mean error, average error, we have to go for mean square error. Mean square error will give us the correct judgment. Always remember that average error or mean will give us wrong estimate. Better to go for any, even in average, like also there will be some plus and minus, we have to go for square. So now, mean square error. Square error and mean average. Now rather taking error function f of t directly, now we square it. Error function square and its area is total area given to t dt and mean is average t put by t time. Now you are taking square error square. Rather taking directly error function, you are making it square. Okay, error square and you are doing it average or mean. What is called mean square error. Now this is, you wrote it as some epsilon, some symbol. Now here, as you see here, just now, this is the mean square error. Error function f of t 0 pi 2 pi. Sinusoidal null function, difference is this. Now you square this. So now f square of t, for all positive values, whatever is here 1, will become again 1. Negative values, minus 1. Whatever is minus 1 square also will become again positive. Minus 1 will become plus, right? Positive. Now you integrate for this interval t1 to t2, theoretically, if you integrate this error plus this error will be added, you will get some error is there. You get the impression that some error is there, hence these two functions are not approximate. a large error is there. These two cannot be approximated. Have not been approximated. Okay. So this is the important concept. Mean square error. So now from here, from this concept, now we will go for another concept called orthogonality. Yeah. So now in the approximation process, f1 of t is approximated into c1 to f2 of t. C1 to f2 of t. Now, the error function f of t is equal to f1 of t minus c1 to f2 of t. Now, here we have to choose a best coefficient or constant such that the error function is minimized so that f1 can be approximated to f2. So here, how to choose this C12? Right? Among these functions, so you might have learned the partial differentiation or maximum and minimum results. Okay? Now we are aiming to this. We have to two partial derivatives is with respect to C12. So from this we calculated error function. Actually we want to minimize error function. Error function is what? 1 by t2 minus t1 integral t1 to t2 fe error function square mean square under dt. By minimizing this, you have to choose C12. So here 1 by t2 minus t1 integral t1 to t2 fe means f1 of t minus c1 to f2 of t by dt. So here it is our actual error, mean square error. Now we have to define or choose the approximation constant C12 such that this mean square error is minimizing. Okay. So here we use the constant rho epsilon divided by 2 C12 equal to 0. This is maximum and minimum principle. Okay. By doing partial derivative with respect to the whatever parameter you are aiming, making this function equal to 0. So now you derivate this entire function with respect to C12 and make it equal to 0, then you can derive. So here, so how you, in this process, I can interchange, see, derivation and integration. Right? So this is basically dou by dou C12, 1 by t2 minus t1 integral t1 to t2 f1 of t minus c1 to f2 of t square dt. This should be equal to 0. Right? Now this is the, you are derivating with respect to t12, that t1 t2 was constants for c12 because you wanted to derivate this with respect to parameter c12, hence t1 t2 was constant. So I will take it out 1 by t2 minus t1, I can take it out common. Then this is dou by dou c12 integral of t1 to t2, all these things will come. Now in this product it is 0. 0 means either this entire thing will become 0 or 1 by t2 minus t2 will be 0. This product is 0. Product is 0 means either this term will become 0 or this term will become 0. This term cannot become 0 because t1 and t2 are some time is there. Some 2 seconds to 5 seconds, or 3 seconds to 6 seconds. This cannot become 0. It should become 0. Now here first I derivate, then I will integrate. Integration and derivation here may be interchange. I can derivate first, then I will integrate. So now if you observe here, see, interchange integration is a t1 to t2 Go by dou C12. See, F1 of t square, okay, minus 2 C12 F1 of t F2 of t plus F2 square, sorry, C12 square F2 square t dt, right? A minus b whole square, a square minus 2ab plus b square. Now, integral t1 to t2, you are derivating first f1 square, so it is with respect to 0. There is no relation with the c1 divided. This is 0. This term will become 0. Then minus 2 is a constant. Minus 2 is a constant. F1 and F2 also constant with respect to C1. So integral F1 t, F2 t, this dt will multiply. Plus here F2 square t is also a constant. Now with respect to C12 square become 2 C12. 2 C12 F2 square t. This is dt. Right. Okay. Here also dt equal to 0. Now this term, this integration is common for both the terms. Integration is common to both terms. Now I will take this term this side minus. It becomes minus. Here already minus is there. Minus will get cancelled. 2 is here. That side also 2 is there. 2 also will get cancelled. Minus 2 both will get cancelled. The remaining is here. C12 is there. I will take it is a constant. I will take it out. So it can be written as like this: C12 integral T1 to T2 F2 square t dt equal to here integral T1 to T2 F1 of t into F2 of t. From here, now we are going to C12 equal to, you keep C12 here, remaining thing you bring that side. Integral T1 to T2 F1 of t into F2 of t dt divided by integral T1 to T2 F2 square t dt. Right? So, this is the way to find out if you have two functions f1 and f2. The best approximation coefficient can be found by using this formula. Such that error is minimized because this expression is derived from the to minimize the error. Those x are right. Those given. So here now we explore the concept of orthogonality now. Now the concept of orthogonality. You see here, when this C12 becomes 0, see, you are approximating F1 of t with C12 F2 of t. If C12 equal to 0, then F1 cannot be expressed into F2, or F2 cannot be expressed in terms of F1, provided when C12 equal to 0. So, when this C12 becomes 0, when the numerator equal to 0, it means integral T1 to T2 over interval T1 to T2 F1 of t into F2 of t dt equal to 0. See, it means when C12 equal to 0 means F1 cannot be expressed in terms of F2 or F2 cannot be expressed in terms of F1 or F1 component cannot be seen in F2 or F2 component cannot be seen in the F1. They are totally independent. Provided this numerator term becomes 0. 0. C12 equal to 0 means numerator is 0. So this concept what we call is here, these two functions are orthogonal to each other. These two signals are orthogonal to each other. Now we have seen vectors v1 dot v2 equal to 0, same 0, here dot product, when two functions, two vectors, one cannot be written in the another. These two are independent. Similarly, functions and signals also. This is what is called inner product. Inner product of these two functions should be equal to 0. So if you draw a function and multiply each component, total will become 0. Inner product becomes 0. Okay. So hence this is what is called. Hence we say that these two functions are orthogonal to each other. So to prove two signals are or two functions are orthogonal, over a interval t1 to t2. If you perform this integration, integral product of these two, use 0, then we can say that those two functions are orthogonal to each other. Means one function is independent of another function. This is the concept of orthogonality we have derived from analogy of vectors. So this means by other. This is concept. Okay. Now, then properties or examples you may use. Suppose for example, sin n omega naught t, sin m omega naught t, over a interval from t naught to t naught plus 2 pi by omega naught. Interval, okay, over a interval t naught to t naught plus 2 pi by omega. T by 2 pi by omega means t, one time period. For one time period, if you say this is sin n omega naught, this is sin m omega naught. So here, these two signals are same type sin but different harmonics. Same signal, different harmonics. Right? This is sin n omega naught, this is m omega naught. Same signal with different harmonics are orthogonal to each other. Orthogonal to each other. If you perform integration, sin n omega naught t into sin m omega naught over a period t naught to t naught plus 2 pi by omega naught dt, f1 into f2. This you do by multiplying the 2 divided by 2 sin a, sin b form. If you expand, you will get cos a minus b minus cos a plus b. Then integration of cos again becomes sin. You substitute the upper limits, the lower limits, you will get 0. Integration will give you 0. This is one property. Property of orthogonality. Property of orthogonality. Second property is different sinusoidal signals, sine and cosine. Now here is same signal with different harmonics. Same now sin n omega naught t and cos n omega naught t. Both are same frequency, n omega naught, but signals are different. Sine and cosine. Also orthogonal. Sin n omega naught t, cos n omega t. Same frequency with different functions are orthogonal to each other. Then third one is a DC signal is a sinusoidal signal. A DC signal is sinusoidal signal. Because my signal f1 of t is equal to some constant a, f2 of t is equal to sin t. f1 of t is equal to some constant a, f2 is equal to sin t, or a equal to some 10 or 100, that is. So if you perform f1 and f2, a sin t over a period suppose 0 to 2 pi dt, you give 0. A is a constant. In the sinusoidal signal, maybe 2, here 2, or 10. This area will get cancelled with this area. So total will be 1 is the opponent of the equal to 0. The inner product becomes 0. Then another important property here is we can use the concept of orthogonality for calculating energy and power of the composite signal. a combined signal. So in the BB, if you see the exercise problems, it is one of the important exercise problem is there in the BB standard. Two signals, F1 and F2, with the different energies like E1 and E2. This is energy E1, this is energy E2. Suppose if you combine these two signals, F1 of t plus F2 of t, may use some other signal F3. If F1 and F2 two orthogonal signals, if F1 and F2 are two orthogonal signals with energy E1 and E2, then if you combine these two signals, the resultant signal energy equal to E1 plus 2. This is, you combine these two signals, energy formula is F of t square, magnitude of F of t square, x square or F square into energy. So energy is here F1 of t plus F2 of t square dt. Right? So which is equal to integral F1 square t plus integral F2 square t plus 2 integral F1 of t into F2 of t dt. It is like a plus b
Whole square.
a square plus b square plus 2ab. So as these two signals are orthogonal, integral of F1 F2 dt must be equal to 0. So when this is 0, it indicates what? Integral of F1 square t energy of the first signal, E1. This indicates energy of second signal. Energy by definition is integral of F square by dt. So similarly for power also, energy per time equal to power. Energy per time equal to, only simply you are adding here 1 by t. 1 by t if you add, it becomes power. Similarly, average power first signal plus average power is equal to total power of a two orthogonal. There is no question of P1 like that. So like this, these are all some of the basic properties of orthogonal. Then I will take these concepts to Fourier series. I will take you this concept to Fourier series. You all know that the Fourier series is any arbitrary periodic function. Any arbitrary periodic function can be written or represents, expressed as a linear combination of mutually orthogonal functions. The definition of a Fourier series is any arbitrary periodic function or signal can be represented, can be expressed as linear combination of a complete set of mutually orthogonal functions. Right? So linear combination means what? Plus addition. The combination is addition. Plus. Linear means multiplying with some constant. What type of function we have to use? Mutually orthogonal function. Mutually orthogonal functions. That too, the important word what we are using, complete set or closed set or complete set of mutually orthogonal functions. Now these words know to describe. Right? So how this definition has come? The Fourier series, the basis for all transforms. Then the Fourier transform, short-term Fourier transform and Fourier transform. These are all the basis functions. That's why this orthogonal concept is important for any transform. So here mutual orthogonal functions. Now similarly, approximation of a function with the mutually orthogonal functions. So here arbitrary function, let us say f of t, is approximated. Earlier only one function is to another function, single function. Now you are using here functions, plural functions. But how those functions must be? They must be mutually orthogonal to one another. Okay. Let the functions of G1 of t, G2 of t, G3 of t, and so on, Gn of t. These are my set of functions, set of orthogonal functions. When you say that these two are mutually orthogonal, G1 into G2, all are over interval T1 to T2. Specific interval for all the functions. G1 into G2 integral G1 D to dt equal to 0. G1 with G3 also equal to 0. G1 into G4 0. Similarly, G2 with G3 or G2 with G4 or G2 with G1 or G3 with G1, G3 with G2, all functions. It means integral T1 to T2 G j of t, G k of t, dt equal to 0 where j is not equal to k. So when this product holds good, then we can say that all these functions are orthogonal to one another. They are mutually orthogonal. If we choose such a functions, if you take such a function from outside to express your function, okay? So this also has come from vector orthogonal space. Any vector can be written as linear combination of unit vectors. Right? Any vector can be written as combination of a n-dimensional unit vector. It's what is called vector signal space, vector orthogonal space. Similarly, here also, signal orthogonal space means earlier only one signal, another signal. Now several signals form a space. Right? So these are all orthogonal to one another. Then we call this space as the orthogonal signal space. So now, my signal I can represent now f of t equal to c1 constant into g1 of t plus c2 g2 of t plus c3 g3 of t and so on, cr gr of t plus and so on, cn gn of t and so on up to n signals. Now I can write my operator signal can be written as the linear combination of several mutually orthogonal functions. Right? So now, as usual, we have to estimate the C12, C13 and so on, Cn of the rest of our functions. How we have derived earlier. Similarly now, same way, you have to define error function. The error function here is f of t, error function, f1 of t minus this entire function I am writing, I will write from r equal to 1 to n, cr gr of t. This entire function r equal to 1, c1 plus g1 plus c2 g2 and so on. So you see this side, this is my error function. Now I have to define the error as usual, least square error 1 by t2 minus t1 integral t1 to t2. This is f1 of t minus summation r equal to 1 to n cr gr of t y dt. I have to now minimize this error signal by choosing proper n coefficients, not one. Earlier only one coefficient. Now here n coefficients I have to choose properly. Right? So here also 2 epsilon divided by 2 Cj. Some I cannot differentiate all. One I can substitute. So if you derivate this equal to 0 as we got earlier. Similarly, here also you get this Cj at any time. J will take values 1 to n. Integral t1 to t2 f of t gj of t dt divided by integral t1 to t2 Gj square of same formula you will get. In terms of C12 there, you can Cj, you are derivative. Suppose it may be n or r, you will substitute. With respect to Gj signal, you substitute f of t, you will get Cj is coefficient. Cr signal, if you use, you can calculate Cr. Cn signal, Gn signal if you use, you will get here Cn. Like that, all coefficients you can calculate. So this is the here T1 to T2 Gj square T, when j is equal to Gj square, this will give some constant term. This will give some constant term, some k, j or kr, some constant value. This is where j, k, when j is equal to k, integral of Gj square T, this term always give you some constant value. Like suppose integral of sine into sine square will give some 5/2, like that. Some constant term will do. So in this way, you can calculate each coefficient and you can represent your function. This is what is called representing a function or approximating function using mutually orthogonal. Now earlier, only one function with another function. F1 of t is approximated into C2 into F2 of t. Only one function. Here now, we are approximating into many functions. So, why you use here many functions? Your error will be minimized. So, error will be minimized. So, now how the error is minimized, I will explain now. So, there is a formula also is there. So, calculate error also you can derive now. It's not an issue. You will feel bored. Now I will explain you graphically how error is minimized so that you will appreciate more. It is more. A rectangular function. Please observe. A rectangular function 0, pi, 2 pi, 1 minus 1 f of t. I can approximate this function using a single sinusoidal function. This is a sine, right? Sinusoidal function. Here approximation coefficient of pi by 4 or minus pi by 4 will come will lead like this. This is sinusoidal function. The rectangular function, now I can write my rectangular function f of t is equal to some constant into c1 into sine t. My f of t is defined as f of t is equal to 1 for 0 less than t less than pi is equal to minus 1 pi less than t less than 2 pi. This is my function for positive values. 0 to pi is plus 1 and pi to 2 pi is minus 1. This is my rectangular function. Now I don't have rectangular function with me to use for the other purpose. I have sine function. How best it is approximated this. Okay. So this is the sinusoidal function I got. Where C12 equal to pi by 4 something. Okay, you will get it. I will mathematically you can solve it at home also. Huh? Yeah, it is pi by 4, right? It is a pi by 4. Pi by 4 means it is 3.14 divided by 4 now. This is like 0.8 something. The maximum value 1 to 0.8. So, this is the error. It is not exactly like this. It is like this, means this is the error signal. Right? This is the error signal. We use rather using rectangular function, if you use sinusoidal function, it's not equal, some error is there. Okay. So that error percentage here, 0.19% or 19% error is there. Rather, using single function, if you use two functions, in approximation, if you use two functions, sin t, sin 3t, means now phi function is f of t is equal to pi by 4 sin t plus pi by 4 by 3 pi. It is 4 by pi, not pi by 4. 4 by pi. It is also equal to 4 by pi. It is 1.2 something. Yeah, it is 4 by 3 pi sin 3t. Sin 3t are orthogonal to one another. As I told you, properties, same function with the different harmonics, orthogonal. These two are mutually orthogonal. So then here the coefficient is defined as 4 by pi. Here the coefficient is equal to 4 by 3 pi. Okay. Now, if you for different times t equal to 0, t equal to 0, sin 0, 0, then also sin 0, 0, you will get 0. T is equal to pi or pi by 6 and pi by 3 and 3 pi by something 2 pi. If you substitute all these values, your rectangular function is this. If you substitute this, you will get the function values like this. It will give like this. If you use only single function, sinusoidal function to approximate rectangular, it appears like this. Same thing, if you use two functions to approximate, your signal looks like this. You can check it for different values of t between 0 to 2 pi, it gives like this. Suppose if you use three functions 4 pi, 5 pi, sin 5t, because for even number of t it becomes 0, you calculate Cj. Coefficients you calculate, Cj becomes 0 for even number of sin. That's why you are taking only odd number, sin t, sin 3t, sin 5t, sin 7t and so on. So now this function, if you see, same rectangular function here, this is, if we use three functions, this is, error is slowly reducing. It is nearer to rectangular function. It is nearer to rectangular function. Suppose if we use 4 functions, 5 functions, 6 functions, it almost are equal to this. Almost equal to rectangular. So it means what? This rectangular function is having this many frequency components in it. If you draw the spectrum if you draw, it has sin t, this frequency component, maybe some omega t, next to 3 omega t, and also 5 omega t, 7 omega t, 9 omega t. These are all different frequency components. So this signal is having a spectrum is discrete for Fourier series or for the periodic signal, spectrum is discrete. Whereas for aperiodic signal, spectrum is continuous.
It is like FM radio frequency.
Yeah.
Some particular temporarily gets
Yes, today it's a rectangular signal. Though it appears as a rectangular, it means this signal can be again composed by adding up several frequency components. Again, you can generate it. Or you can assume that signal is had that many frequency components in it. That many frequency components. So, like that, if you take as a number n increases, as I taking 4 or 5 or 6 or 10 functions, if you take, this will become very closer to your rectangle. This error, mean square error will be reduced as number of functions increases. As number of functions increases, mean square error decreases. Here provided these functions are orthogonal to one another. Important thing is these functions must be orthogonal to one another. Now another concept here is, now slowly I am going to Fourier series. And here closed or complete set of orthogonal functions. Now closed or complete set of orthogonal functions. Why this adjective? Closed or complete set. So as you have seen now, as n increases, number of terms, the number of orthogonal functions, error is minimized. Error is minimized as you use more number. Now if you use infinite terms, if you use, then it is exactly equal to whatever function you are estimated to approximate. Now, then your series will become now infinite series, right? F of t equal to C1 G1 of t plus C2 G2 of t plus C3 G3 of t and so on, infinity. Now, infinite series. Because to minimize error equal to 0, so it is here infinite series. So this is small f of t equal to summation n equal to 1 to infinity C1, CR GR of t, CN GN of t. CN, here you have used n, CN GN of t. This is it is what is the, now we can say that it is an infinite series. This series will converge, okay, provided you are taking the coefficients. Now, these G1, G2, G3 all are orthogonal functions. Now here, why you are using complete set? This set must be complete. This set should be complete. So, what the definition has given, the complete set, just note down, I will read out the typical job count. A set of functions G1, G2, G3 and so on, GR of t, mutually orthogonal over interval T1 to T2 is said to be complete or closed set if there exists no function x of t for which it is true. Which is true, integral T1 to T2 x of t gj of t dt equal to 0. There exists no function x of t. Suppose, I got it? Idea? G1, G2, G3 and so on are mutually orthogonal functions. Integral of over a period T1 to G1, Gj of t, Gk of t equal to 0. This is orthogonal functions. Right? Now, suppose for example, I will tell you like this. Sin t, sin 2t is orthogonal to each other. Sin 3t is also orthogonal to sin 3t, sin 2t. Sin 4t is orthogonal with sin t, sin 2t, sin 3t. Suppose one of you says that this is a orthogonal set, orthogonal function set. Now, I will give you sin 5t. Sin 5t is also orthogonal to each. So, without this sin t, you cannot say this set is a complete set. Sin 5t is also orthogonal with sin t, sin 2t, sin 3t, sin 4t. So, without sin 5t, these four functions you cannot say that they are mutually orthogonal. So, no function x of t exists in this relation. Also, so that is why, that is the reason, the basis for Fourier series is not only sine is also orthogonal with the cos. Cos t, cos 2t, cos 3t, cos t, cos sin t, this is also all are orthogonal to each other. So that is the reason the Fourier has written any periodic function can be expressed as f of t is equal to summation n equal to 0 to infinity an cos n omega naught t plus bn sin n omega naught t. This is the definition of Fourier series. If you expand n equal to 0, here 0 equal to 1, here equal to 0. A0 plus A1 cos omega naught t plus A2 cos 2 omega naught t and so on. V1 sin omega naught t plus V2 sin 2 omega naught t and so on will go up to infinity. It is a linear combination. This combination is plus. Linear means multiplying all this A1, B1 and B2 are some scalar quantity. Some coefficient as we have defined this C1, C2, C1, C12 the coefficients. Similarly, these are the coefficients. Here cos omega naught t, sin omega naught t are complete set of orthogonal, not simply mutual orthogonal. It is a complete set. Suppose if you miss here cosine, it is not a complete set. Because without the cosine, this cannot become a complete set. Suppose if you miss here sin 2 omega t, without sin 2 omega t, this set cannot be complete set. So Fourier is defined, Fourier series is a representation with a linear combination of complete set of mutually orthogonal functions, not simply mutual orthogonal functions, complete set of mutual orthogonal functions. That is why without sine or without cosine, this Fourier series is incomplete. That is the reason using Fourier series you have to produce both sines and cosines because we form a complete set of orthogonal functions. Right? So with the complete set of orthogonal functions, this is the definition. Suppose here without means no function exists like x, no function exists like a cos or cosine. Form a complete set.
This series is starting A0 by 2
Yeah. Now I will explain it. What is this an? An is equal to an is a coefficient. As I told you, C12 like an equal to what? Integral T0 to some T0 plus T. F of T. F2 means here what? Cos n omega naught T. Cos n omega naught T dt divided by F2 square. Integral of T0 to T0 plus T. Integral of F2 square means what here? Cos square n omega naught T dt. Right? This cos square n omega naught dt will become d by 2. This will become this integration. This will become d by 2. Okay? This integration d by 2. This is 2 by t integral T0 to T0 plus t f of t cos n omega naught t dt. Here, first term is dc term, where n equal to 0. If you substitute here n is equal to 0, cos 0 equal to 1. So this is 2 by t integral T0 to T0 plus t f of t. This is average value. Whereas for other values, A1 cos 1 t, it is common t by 2. Similarly for Bn is equal to 2 by t integral T0 to T0 plus t f of t sin n omega naught t. Where this 2 by t means what? Integral of sin square n omega. So sin square. Okay, if you integrate, you will get some value, some pi by 2, some t by 2. This is the how see even this coefficient and this coefficient also we got from the concept of orthogonality and approximation. That is the basis for Fourier series. Similarly, not only for this real functions, even imaginary functions, also orthogonality for imaginary functions, imaginary orthogonality is also similar. Orthogonality for imaginary functions. Suppose e power j omega t, e power minus j omega t. These are all a complex functions. Complex functions also same. But thing is, one of the functions you have to take is the thing, its conjugate. So this is F1, this is F2. So I take one of the functions in conjugate form. It means its orthogonality over a period T1 to T2. F1 of T, F2 conjugate T, Tt divided by integral of T1 to T2, F2 of T into F2 conjugate Tt. Earlier here F2 square we used to write, same F2 is conjugate form. This is the approximation to complex functions. Okay. So similarly to this concept, then we go for exponential for instance. Here we use complex exponential. Rather we use trigonometric function, sin and cosine. There we use e power j omega t. So these are all some of the brief description of the concept of orthogonality. So I am winding up here. So if you have any queries, please raise your queries. Just I would like to give the concept of orthogonality and how it leads to Fourier series. The Fourier series are developed where AN and BN are the concept of orthogonal coefficients and orthogonal. Why you are using only? Why don't you use only sine functions in the Fourier series? Why don't you use only cos functions in the Fourier series? Because only if you use sine, it cannot be called a complete set. Only cosine if you use, it cannot be complete set. Otherwise, you want to have a complete set to minimize the error of the infinite series representation. You need to use both sines and cosines. And for your information, the basis functions for the trigonometric Fourier series are sine and cosine. It need not be always sine and cosine also. Some other also. So, this is exactly what leads to the Fourier transform of small some waves having some orthogonal property also you can express. You can also create your own transform also by taking small waves, some basis function. Provided you have to prove that those functions are orthogonal to one.
What curious I have, suppose two vectors are there, one is 0 degree and another is 135 degree. Can we say they are orthogonal?
Who is orthogonal? This one cannot you can say orthogonal.
How that system is resolved? Vector which is 135. One is at 0. How that system will be resolved or that vector will be resolved?
Resolve, suppose if you want to treat as a horizontal, using the theta, that you let us say it is from A cos theta, you can write horizontal component. Similarly, A sin theta you take, you get the vertical component. How you want to visualize that? You want to see the component in the horizontal, you get the A cos theta. Any other? Okay. You can stop here.